Okay, so the final part here is going to be about proving and solving using some new identities. And these identities are all going to derive from the year 12 identity that was so important, sine squared plus cos squared is equal to 1. So if I divide this identity through by cos squared x, I will get the following identity. So sine squared divided by cos squared is going to be tan squared. Now, some of you might not be too happy with that statement, but the intuition is this. So we said sine squared divided by cos squared x. So you could take out the power on that. And I encourage you to just see that if you expand it, it is equivalent. So in the bracket then, you've got what? You've got tan x. So it is tan x squared. And this is how we write it, okay? We write the 2 in between. So sine squared divided by cos squared is tan squared. Cos squared divided by cos squared is clearly 1 because you've divided something by itself. And 1 divided by cos squared is sec squared for similar reasons to what we said on tan. Remember that sec has its third letter is c, so that kind of makes sense. 1 over cos squared is sec squared. Now, you've had one of the new words, one of the new functions here, sec. So there's 2 missing that we learn about, cosec and cot. So they must be in the other identity. And you get this if you take the same starting line and instead you divide by sine squared. Sine squared over sine squared is 1 again. Cos over sine is cot, so cos squared over sine squared is cot squared. So the tan bits, whether that's tan or cot, are always on the side of 1. They're always with the 1 piece. Sec squared, so it's no surprise really that we've got our final function here, cosec squared. So this identity really is incredibly important, and you can sort of derive in your head or otherwise these other identities, which we're going to practice now. So before I show you the final question, I just need to remind you about something called the difference of 2 squares. So the difference of 2 squares you would have seen before, maybe at GCSE was something like this, okay? Can be factorized as such. You can also do it with higher powers, so you could do something like, I'll do a number again, so you could do something like this, okay? Or maybe we could even have something like this, okay? Which would also be quite similar. So this is an important pattern to look out for. So the giveaway is a different symbol, just 2 terms, and thinking of them both as, well, they will show themselves as very much sort of square numbers or terms with an even power here, but that's the way forward, okay? So you're going to see this in just a moment. So here we go. Here is the question. We're going to prove that cosec to the power of 4 minus cot to the power of 4, so there we go, that's that pattern we were just talking about, is equal to 1 plus cos squared over 1 minus cos squared. I've just changed that there, that was a small mistake, it's meant to be a theta. So what was that pattern we just talked about? Well, you're going to start then, aren't you, by writing this as cosec squared theta, cosec squared theta, because if you multiply them, you get cosec to the power of 4. Let's get rid of that. And then the other bit is cot squared theta minus cot squared theta there. Okay? So anytime really we've got these functions like sec squared, cosec squared, cot squared, we need to be a little bit wary of this now because of the identity that we just talked about. I suspect this identity in green might be useful. Not in the way it's currently written, But what if I were to subtract this from both sides? I would get 1 equals cosec squared x minus cot squared x. A bit like when we had 1 minus cos squared is sine squared before, we've got kind of something with this version. So if I see this anywhere, it is the same as 1. Well, in fact, I see it now. It's there. So all of this is in fact just 1. And it leaves me with this bracket to do some work on. I'm going to show you the remainder of the working out because this is now a proof question about this part here. So I've done the difference of 2 squares. I've cancelled this because I recognise that that is 1. I need to be able to spot this. The signals in the question of reciprocal, trig and squared and co. I need to spot this in order to be able to do this. If I don't, then I am going to be stuck. Then I've written them out in terms of sine and cos again. I put them into one fraction and I have the correct numerator already, but I recognise that sine squared, which is what I've got, is the same as 1 minus cos squared. I think we just talked about that. And I recognise that by looking ahead at the answer that I need to get. Let's practice that one more time, but let's do it with a solving question now. So I want you to take a look at this situation here and have a think about how we could get started. So it features cosec squared and it features cot. Now, that identity from before in the green there has cot squared and cosec squared in it. Well, if I'm trying to solve this, it looks a bit like a quadratic. So I might move everything over to one side. But the problem I have is I have different trig sort of pieces there. So cot, this one's going to be quite hard to change. But cosec squared, I know an identity about that. And the identity links to cot. So I could use the identity in green there to change this equation that I've got now so that it is only about cot. And the way I'm going to do it is I'm going to change cosec squared to be about 1 plus cot squared. So I'm going to show you a slightly neater version of that now. So here we go. I've moved everything to one side and I've put the piece that I'm going to substitute there in the green brackets. Using my identity, I know that cosec squared is the same as 1 plus cot squared. If I multiply things out, can you see that this here is very much a quadratic? I've got 4 lots of something squared minus that thing minus 5. Hopefully you just spotted there that you need to make sure you expand that correctly. Equals 0. And then I can solve this like I would have solved quadratics before, like you solved quadratics maybe with trig pieces before, and so on and so on. And I would do it by trying to put it in brackets would be my first port of call. So this could be turned into 4 cot theta minus 5 multiplied by cot theta plus 1 equals 0. Then, once you've done that, we can solve these different pieces. So if I solve this bracket here, if this bracket is 0, I'm going to get cot theta, move the minus 5 to the other side, 5 divided by 4 equals 5 over 4. And we solve this like we did earlier in the chapter. And for this one here, move the 1 to the other side, cot theta equals minus 1. And I would solve that as we did earlier in the chapter. So the identity can be used as well to manipulate equations such as this, so that they only have one trig function, a single trig function, not 2 here, sorry, a single trig function which became cot. That's the goal. And then we can solve these as quadratics. And if you do that, remember, do the reciprocal, and then you just solve from there onwards. Okay, so that's another use of the identity. We can use it for proof questions. We can use it for solving questions. Sine squared plus cos squared equals 1 gives us tan squared plus 1 equals sec squared, and also 1 plus cos squared equals cosec squared. It's time to have a go at the final test your understanding, and I will go through the question one more time, and I will show you the answer to this one here. So pause the video and have a go. So you hopefully spotted that this question is really about sec theta, and tan squared theta is the part that needs to change. My identity that links these things together is 1 plus tan squared theta equals sec squared theta. So if I write out the question, 3 sec squared theta plus 3 sec theta, no problems with that at all yet, don't mind that bit there, equals 2 sec squared theta. Sorry, it's not 3 sec squared theta yet, it's 2 tan squared theta. So let's use the identity before to change that. Tan, if I wanted to get tan on its own here, the 1 would have to go to the other side. So tan squared x, so tan squared x, or tan squared anything, is equal to sec squared theta minus 1. And that result now is going to be substituted in. Okay, so I'm going to do 3 sec squared theta plus 3 sec theta equals 2 lots of sec squared theta minus 1. And I'm going to expand this out and collect everything together. So I'll have 2 sec squared theta minus 2, and then I'll move everything to the same side. 3 sec squared theta, sorry, no, I won't. I'll have 1 now, won't I? So I'll have sec squared theta plus 3 sec theta plus 2 equals 0. Okay, and then with this one here, I'm going to solve this like I did before. So think about how you would solve x squared plus 3x plus 2 equals 0. And I'm going to do the same thing, except I won't be calling it x, I'll be calling it sec theta. So I'm going to jump ahead now and show you the final solutions. So we use the identity here, we have our equation, we factorize it, and then we solve the two pieces. The first one here says sec theta equals minus 2, which turns into this one, and here are our answers. The second one here turns into sec theta equals minus 1, and will turn into cos theta equals minus 1, and there's your final answer there. Okay, there is the other question as well. The other question, I will just show you the solutions to this because it's very much the same sort of thing. So cot, this is a question about cot. You need to use an identity to remove this piece here. When we get to this point here, we're already on lots and lots of marks. We're factorizing to solve. And you'll often get quite a lot of solutions with these ones here. You might remember that again from your year 12 trigonometry. So that is sort of really the core skill of some of the harder quadratics that we will be trying to solve. And it's all about using the identities here to put them in terms of one trig function.